Really?
Yeah, because it sleeps 6 people.
All right, so the clicker's not working, but I'm going to get started anyway. So my talk today is fostering reproducibility, replication with tangible student outcomes. So when I think about the 3 R's, I don't think about reading, writing, and arithmetic. I'm a research kind of guy, so my 3 R's involve research, replication, and reproducibility. So research is basically applying the scientific method to learn something new. And replication is using someone else's methods in a slightly different situation, maybe with a different population, at a different time, to basically see if you can come up with the same type of results that they did originally. So replication is really crucial in the scientific endeavor, because without replicating the earlier studies, we can't really be sure that we haven't just made a type 1 error. That's an error where we said that there's something there, but there's really not. And I differentiate between replication and reproducibility. So I think about replication as using the same methods in new ways. But reproducibility is taking someone's existing data set, using their same type of analyses, using those analyses on that data set and coming to the same numerical results, same types of figures, everything else. There's some, I don't know, a lot of people in the literature right now are talking about reproducibility as if it's both of these things, but I like to separate them out, because when people talk about, well, I performed a replication, they're usually talking about a study as opposed to just cruising through someone's data. So these are my 3 R's. And what's the big deal? Why are these such a big thing in my mind? I don't know if you guys have seen this guy before. Have you guys heard of Diederik Stapel? So about 3 years ago, he set psychology into a furor. Does anyone know what happened? It was in the news. Turns out he had like 55 of his papers were fabricated, falsified, I mean just huge. And psychology just went nuts. And I believe it was a graduate student of his that uncovered the academic dishonesty, because the data for some data sets looked just a little bit too good. When you're used to looking at data and seeing natural variability, there's sometimes that things pop out. This just looks too clean, too good. So Diederik Stapel, after this whole thing came out, a lot of people started talking about what can we do to foster replication and foster reproducibility. But this isn't just a psychological phenomenon. So this individual, he's a plant compound researcher, so that's fancy for biologist. Kyung-In Moon, he ended up having about 33 of his papers retracted, and it's not clear whether he was fabricating or falsifying a lot of data, but what he was doing was he was submitting his articles to journals, and then when they asked you to suggest referees, he was suggesting made-up referees that would be directed to him. And they figured this out because those of you who have tried to publish in peer-reviewed journals know you send out a paper, you get a letter back, okay, it's been sent out for review, thank you very much. And what do then? You wait for the reviews to come in. And this guy's reviews were coming in like an hour after they were being requested. It's a little bit suspicious. So we have this problem with academic dishonesty in psychology and biology and all sorts of disciplines. And not just that, recently there's been some news why most published research findings are false. And this is more domain general, I guess. The idea is that there's a lot of stuff out there that's false. And any of you guys know why that is? Why there'd be so much stuff out there? It's crap. You have to make a livelihood, right? Publish or perish. You don't publish, you don't get the stuff. So there's incentives to massage if you need to. There's incentives to, oh, we don't have a significant result right now. Maybe if I collect 5 more data points, it will be, significant. Oh, it's still not. Let's just get a little more. Or let's grab a whole bunch of different observations, on tons of different variables, and we're going to look for the ones that actually correlate significantly. So, I've looked at 100 variables, and by chance, 5 of them are correlating at a statistically significant level. Let's not report that I'm looking at all 100 of these. Let's just report on these ones that I found and get results out there. So there's a lot of things that are going on that really aren't great for the future of science and thinking about some of the current debates within Senate about climate change. Right? Oh, you can't use the word climate change. There's no such thing as climate change. It's not real. Look, I have a snowball in my hand, and it's freaking, I don't know, do you guys remember that, the senator? And it's like, yeah, but if you look at the other part of the country, if you look at the world as a whole, things are different. But there's a lack of trust in public science. And for me as a scientist to help my students understand that there's a lack of trust and why there is this reasonable lack of trust and what we can do to increase the public trust. What types of things can we do to avoid this type of a thing in the future? One final note, Brian Nosek, he's, I believe, at the University of Virginia, and he's one of the co-founders for the Center for Open Science, which is this wonderful web site that connects to a platform. I believe it's the Open Science Foundation, where individuals can put up a project that they're working on before they've collected any data. They can make their data available, they can make their materials available, they can do everything to make the process as open as possible. And he is also someone who started this mini labs replication project. So in psychology, there are some key findings that maybe hadn't been replicated that people were just relying on and teaching as the truth for years and years and years. So they started this mini labs replication project where you have lots of labs, hundreds of labs across the world, looking at some of these foundational pieces within psychology and trying to replicate them. And it turned out that almost 2/3 of these important things haven't been able to be replicated. That's bad. So, beyond scaring my students and beyond scaring you, why do I teach this stuff when I do teach my students? Oh, it's working now, hallelujah. So one of the things that I want my students to be is skeptical. And I feel so bad because back in my more naive days, let's say 5 years ago, I was thinking, you need to be really skeptical of what's out there in the popular literature. You need to be skeptical of the research literature, of the peer-reviewed literature too. Think about it. Does this make sense? Do these data really support things? But in general, I thought, on the level of skepticism, maybe you don't have to be as skeptical when it comes to peer-reviewed stuff. But from the bulk of the data, it looks like you need to be just as skeptical of that too. So I want my students to be skeptical and think about things and try to think critically to determine for themselves whether or not the things that they're reading are likely to be the truth, and even better, what they could do to test those ideas and replicate those studies to come to a better understanding. Another thing that I like to do is, I think of myself as a scientific evangelist, and I feel like when I'm in the classroom and I'm teaching my students about these concepts, it's helping them to understand not only why these things are a danger, but why it would be important to put safeguards in place to demand open access to data so people can look at the actual data as opposed to just the results of some analyses. So I'm looking for increased skepticism, increased demands for accountability, and a willingness to avoid these same problems if they're going to be going on to graduate school or into industry. A willingness to open up their materials, a willingness to open up their data, which can be a scary thing. I mean, if you're publishing and maybe, let's say, you're doing something a little bit out of your comfort zone, are you doing the tests exactly right? You've read it, you think you know it, maybe you've even talked with a colleague, but by putting your data and your analyses up there, someone who knows more can easily come in and say, you did this wrong, and that can be embarrassing. But it's something that's important and I think really necessary. So how can we address some of these problems? So I think the biggest thing that needs to happen is a lot more open access. So open access to the materials. What was the exact survey that you're using? I know in psychology there are lots of proprietary materials, intelligence tests or personality tests, and some of those are not openly available for good reason. If everyone had access to them, you could figure out how they're scored and then potentially figure out how to respond to that test if you're in a job interview and they're giving you one of those types of surveys. But in other situations, it would be important for others to have access to your exact materials. If they have exactly your materials, they can do almost exactly the same study at a different time, in a different place, or with different participants. Also open access to protocols, exactly what happened, the timing, who did what. All this information that's related to the actual conducting of an experiment. Also having open access to data, as I've already mentioned several times. So not just here are my materials, but here are the results that we've come up with. Here are all of our data. Have fun. Look for things that I wasn't thinking about looking for. Also, having open access to the analyses. So if I'm going to report a t-test, and I've got a t-test done in R up here for you, Kelly. So if I'm going to report a t-test in a journal, I can say, you know, I did a paired t-test, and it was this value, and p is less than 0.05. But was I assuming that variances were equal? Or was I assuming that variances are not equal? For those of you who don't know about statistics, that makes a slightly important difference. And without access to the actual analyses, some of those more low-level details might not be there. And then if I was trying to reproduce the same results with your data, if I don't have access to that lower-level information, I might not be able to reproduce what you have. Also, open access to publications. So there are now movements to open up, I think, +1, having these massive online repositories for lots of different disciplines where people will have free access to the journals. They are making, other journals are making authors have the ability to pay a certain amount, and then that article will be open for everyone. And if you're at a big R1 institution with big old grants, it's not a big deal to throw a couple hundred or maybe 1,000 or two to a publisher to get your article out there. But for someone at EOU, maybe we don't have that type of funding, especially if we're not on a grant. So publishing in open access journals is important. And finally, one of the things that I really like are open source products. I like open source products because using open source products necessarily means that the things that you're doing are open access. I use R in my class, which means that if I have a data set and I do R analyses here, anyone in the world can download R and run the same analyses. But it's not the same thing if you're using SPSS, MATLAB, or SAS, Minitab, these things that you have to pay for. Now, I could make my analyses available, but only the people who are willing to pay for it already have it or will pirate the software could be able to reproduce my results. So I like to stick with open source things when I can. So in my lower level courses, thinking lower level in terms of not capstone experiences, I am having my students use some open access ideas, open access to data, open access to their analyses. And this part of the open source is related to open source so anyone can reproduce their results given their data. For the upper level capstone experiences, I have them do all of this. So I make them make their materials open, their data are open, their analyses are open, even their presentations, their final capstone experience, here's my poster, is open. And so anyone can potentially replicate and reproduce what they've done because they have access not only to the data, the analyses, but also to the materials and protocol. So how do I do this? Well, my students, they use non-proprietary data formats, or file formats. I'll talk about what some of those are in a second. We use R, which is free open source software, RStudio, free open source software, Git, free open source software, and Github, which is an internet that works very well with Git, as you might imagine, given the similarity of languages. So the data files that I have my students work with, they're just plain text, comma separated values. You guys know what comma separated value files are? So they look basically like this. First line, you might have headers, so there's an ID, some condition, and response time. And then you have on the next line, participant number 1 in condition 1, they had this response time. Participant 1 in condition 2 had that response time. So the data are all logically arranged in a plain text file that you can open in a number of ways. You can open it in Excel if you want to. You can open it in Notepad. Go Microsoft plain old generic Notepad. I wouldn't recommend doing this. That's a nightmare. Or you can open it in Notepad++, where things are much more neatly aligned. Now these data are all data from an experiment, I believe, I don't want to say if it's the wrong one. Pearson, I think it's Pearson. Cengage is going to kill me if this is a Cengage product. So in my cognitive psychology class, my students have the ability to participate in some experiments online. And then their results, as well as the results of hundreds and thousands of students from across the world that are doing these online experiments, can be collated and downloaded from their site. So these are data, real data from a real online experiment that I have my students analyze as part of the lab component of the course. So the analysis files are also just plain text. It uses a format called R Markdown. It's plain text, but we have some special characters that when the R Markdown file is processed, it's going to indicate to the processor, oh, we want to make this bold, or italics, or this is a hyperlink, things like that. So it's plain text plus some special formatting and also some special sequences for analysis code. So here's an example that I created this morning for SIIT. You can see this is just on Notepad, and this in plain text looks fine. Wish I could zoom in a little bit. But you'll notice there are these like 3 hyphens up here, 3 hyphens down here. This is going to demark this for the processor. This is special title type information. Here I've got a pound sign, which is going to indicate that this is going to be a title. Here I have an actual HTML comment, which lets it know that this is a comment, so don't put this in the output. Then I have just some regular old text explaining what I'm doing, and then I've got this special little code, this tick, tick, tick bracket, R bracket, with data. I'm sorry, not data, but with R code that's going to be used to run the analysis. So we have this plain text code, but RStudio knows how to deal with this plain text code, and it will do something special, which I'll show you in just a minute. So we've got plain text CSV files that anyone in the world can open. We've got plain text R Markdown files that anyone in the world can open. Nothing's proprietary. Then we've got our open source analytic tools, and for me, this is R. R is amazing. Here's what R looks like. Students freak out when they see R, because instead of SPSS, where you click, click, highlight, click, click, this you have to type, type, type. And they're used to watching movies like The Matrix, where you see the hacker guru, and what are they doing? LSCD, I have no idea what that is. The commands freak them out. There's a learning curve, but there's a learning curve to learning which buttons you have to press in SPSS, or how to type in in Excel, right? Equals sum whatever divided by whatever. So I try to get my students into things very slowly, and thanks to Kelly and SIIT too, I'm on my way to making that process easier by putting some helpful screencasts up online. Anyway, so this is RStudio, I'm sorry, just R. And in here I have exactly the same code that I showed you previously. So here it says SIIT1 ratings. Look, these are totally real, non-made up data. They're made up. Yeah. So I made up some SIIT1 ratings based on a normal distribution with a mean of 2.3 and a standard deviation of 0.7. And then SIIT2 ratings, that's us. We have higher ratings, a normal distribution with a mean of 3.4 and a smaller standard deviation. And then I have a t-test. There's nothing here special in the text. But if we run that code inside of R, it will give us the result of the t-test. And what is it? Oh my goodness, highly significant. SIIT2 is much more popular. Yes. Anyway, working in R by itself is a scary thing. If you type things the wrong way, it won't work. Which a lot of students mess up so easily. You might notice this says small t period, small t test. If you type in a big T, it's not going to work. If you miss that period, it's not going to work. So it's really anal. And R by itself isn't very helpful in getting students up to speed and working with their data in a more enjoyable way. So how do I reduce the learning curve? That R inside of brackets is one of the symbols that R uses. It's for people to know what it is. Let me reset the stopwatch. There we go. Okay, so how do I reduce the learning curve? I use RStudio. So RStudio is an integrated development environment. If you're in a computery stuff, you know what that is. But basically, it's a place where R lives. So R lives down here. And up here, we have that RMD plain text file that we were working with earlier. So you have the file that you're working with. You have R doing its stuff. You have a spot where help can come up if you ask for help. You have a spot where it will produce graphs. So this is a bar plot of the SIIT ratings. And most of us are in here at about the 3.2 range. And this is Vicky, but she's of course a bit biased, so she's the outlier here. We also have something that tells us what variables we have loaded up and available to us. Because a lot of times students will say, analyze these data, but these data don't exist. So they can see up there whether SIIT1 ratings and SIIT2 ratings are actually there to run a t-test on. So R makes things easier. It auto-completes. So as you're typing in box plot, it fills that in so you get the correct format. If you are trying to type in SIIT1 ratings, it recognizes that you're typing something that's in your environment. It will auto-complete that for you, which is lovely because if you look at this, you have these ridiculously long variable names. Are you left-handed or right-handed question mark? So in R, if you wanted to access that column, you have to type that exactly the way it is with that question mark at the end. That's a pain in the butt. It's really easy to make a simple mistake. So by having the auto-completion, that really reduces the learning curve quite a bit. All right, so we're using R inside of RStudio, and let's knit it. So remember I said that we can process this plain text file? This process is known as knitting it, and there's a little button up there with a ball of yarn and a knitting needle, and you click that, and what it does is it goes through the code, and it leaves out the comments, it bolds what needs bolded, it recognizes the R code, processes that code using R, and will put that processed code and the results of that code into a nice document. So let's knit it and see what we get. So this is the original, right? That's the original. You guys have seen this before in just plain text. Oh, one other thing I want to point out is that RStudio, it helps make things obvious what are titles, what are comments by changing the color. So it's easier to work with than just Notepad itself. So there's the plain text version, and this is the knitted version. SIIT 2015 comparison by me, which SIIT is better? These are totally real, non-made up data, so my comments are gone, but my explanations are here. Let's compare them with the t-test. Here are my data, here's the t-test. Here's the results of my t-test. SIIT2 rules, clearly. So how do I use this in my class? I mean, I'm making my students do this. In what context? In the context of lab reports. Instead of turning in a physical copy of a lab report, they can explain their protocols using just plain old text. They can show me what the data are. They can run their analyses. And they can also create graphs as well. We could put a box plot in here or, a scatter plot if we wanted to. So very easily, my students can submit this to Canvas. I have my master key, and I can compare the graphs like that. It's very simple, very easy for me to work with. Okay. Does anyone in here use LATEX? All right, well then maybe this isn't that exciting. LATEX can be used for creating documents, and here's a PDF that I created inside of R. I'm writing my own textbook for research methods, and so this was completely created in R. It has links, all of that stuff can be done using R. So if you know more things, you can really get a lot of stuff out of R. So why R in RStudio? It's free, open source. When you think about a student budget, nothing's better than free. Actually, that's not always true. If this were a really crappy product, I wouldn't be recommending it. But it's not a really crappy product. It's a very, very powerful product. And it's extensible, meaning that you can add things onto it to make it do things that maybe you couldn't do earlier. So by itself, you can't create PDFs just with R. But by adding some other things in, you can. It's also hot. Tech companies love this stuff. I have a friend who was recently employed at the University of Denver. He quit. I believe he got tenure and he quit. Why? He got hired by a firm to go teach people how to use R. He was making way more money than he was there. This is great for analytics. In higher ed, I think this is more probably discipline specific, but R is very heavily used in like biostatistics, psychology. MATLAB is also very popular, but R is free. Yay. Okay, so anything besides these two that I have my students use. Well, as I mentioned, R and RStudio, these are what I have my students in my lower level classes do. To analyze data, generate reports for me. In my upper level courses, I want them to open access to their materials, to really open access to their data. And how do I do this? I use Git. So Git is a version control system. This is a very computer science-y thing. Basically what it does is it monitors files and tracks changes in those files over time. Now, this can be useful because if you are running analyses, and I've done this back before I was using Git, I would run an analysis and then I would find something, I'd be like, sweet, this is great, I can publish this. And then I would hit close and I forgot to save the file, and or maybe I saved the file but then later did something, wrote over it accidentally. If I had Git installed, I could have went back to the earlier version that I had saved. So this is great for tracking changes for things. It's free, open source. Github is an internet repository for Git-tracked projects. So a Git-tracked project can be practically anything. It could be a student's art portfolio, although if your student is an art major, I would imagine that a more appropriate location to house their stuff would be DeviantArt as opposed to GitHub. But for data analytic types of things, GitHub's a great place. So I have homework on my computer. This is tracked by Git, that's that .git thing right there. So it tracks any changes. As I update my instructions, it will automatically be saved when I tell it to. And what I can do then is take this Git tracked homework that's on my computer and push it up onto the internet, onto GitHub, so it's available for anyone in the world to have access to. So my students have access to this. If someone in some other place liked my materials and wanted to use them in their course, they can do that. They have complete access to it. So my homework, it's on my computer, it's up here. I can sync the changes so the students are going to see the new thing. And there's some other cool things too. Students can get this. So from my webpage, they don't need to just download the files onto their computer, but they can fork a project. So forking, imagine my project is going in this direction, and then students want to take it in a slightly different direction. Or maybe another instructor likes my materials but wants to cover some analysis that I'm not doing. So they take my materials and they create a new path or a new branch for things. So all of these represent student forks. Most of them forked the data on the day that I released it, but some of them took a while before they actually downloaded things. So students can get this stuff and then they can do the homework on their computer and then push their homework back up to the web server where I can make sure that they've done things correctly. They can also get their original work out there. So this is actually a student capstone project from this spring. So they created their own repository on GitHub. They ran their analyses, they collected their data, they created materials, and what they did is they created this lovely organization, so their data are housed within data, materials are in data. The presentation, that's their capstone presentation, the poster. So anyone in the world who is interested in doing what they did, trying to either replicate it by taking their materials and doing that again, or trying to reproduce the results, you have access to their data, their analyses, and all the materials that they use. So this is awesome. So good job, Dominic and Michaela. One thing I should mention, so this is on the web. So this means that people would have access to your name if you put your name up here, right? And so I told all my students, when you sign up for GitHub, anything that you're pushing up there, talk with your partner. Only put your name on it if you want your name on it, if you want people to know that it's you. And I told my students at the beginning of the semester, if you're going to work hard, put your name on it. If it sucks, take it down at the end of the semester. But if you're going to work hard, put your name on it, take credit for it. Because I think that there are some great reasons for doing this. Students have chafed at this, and I'm working to make the process easier. They ask me, or they tell me things like, it's a pain, because they're not used to typing in commands. They're used to pointing and clicking at things. They say, what does this have to do with blankology? So for me, it's psychology. Git, this is computer stuff. What does this have to do with psychology? Well, it has to do with increasing access to our data and to our results, with making things more transparent, which should increase trust in science as opposed to decrease it. And I get this one a lot. I don't know how to program. I'm a psychology student, not a computer science student. I haven't done this. I tell them it's okay. Really, you're not programming. You're not doing if-then loops. You're not doing for statements. You're just saying t-test, ANOVA. It's not real programming. But there are some amazingly big benefits to this beyond the things that I've already talked about. And this is one of the reasons I am doing this in my capstone. So imagine the students that want to go off to graduate school, and they have their statement of purpose. You know, I want to go to your school, you're really cool, I have some skills, I designed an experiment when I was an undergrad, and I collected data, I analyzed it, and I made a presentation, whoop-de-doo. Of course, it's stated a lot nicer than this, right, in their statement of purpose. But in addition to saying this, which all statements of purpose are probably going to have, they can also say, you can see my entire project here. And so if I've got 2 students and they both look good, and I'm not sure, you know, I've got 1 slot, and they both said that they've done these things, and I can see what this person has done, if they've done it right, I'm going to be more likely to go after that person. So most students aren't going to go to grad school, and that's a great thing because there aren't a ton of jobs out there in higher ed if they want to get the PhD and do this type of a thing. But they can also put stuff on their resume. So in their special skills, I told all my capstone students at the end of the semester, in your resume, you can say that you can use R. You can do data analysis, create graphs, figures, tables in R. You know how to use RStudio, you know how to use Git, you know how to use Github. But not only can they say this, which anyone can say, they can also, you know, say, you can see examples of my work. Here it is. Where an employer can actually go and see, can they do the analyses that I'm looking for? They say they can do this. Or, you know, are they doing the right types of analyses in the right place? So it's a fantastic tool, not only for increasing transparency, but also giving students something really, really tangible. I'd like to thank Rosemary for this idea. I think it was at a union meeting when she was talking about e-portfolios. And I'm thinking e-portfolios, you know, that sounds like an artsy thing or a literature thing. What's that going to have to do with psychology? And then I took a couple courses online through Coursera where I used Git, and it automatically became apparent how I could do something very much like an e-portfolio that would benefit students in the sciences. So if you'd like to learn more, there's my email address. Thanks.